Hi, and welcome back to Codex. Our talks this summer feature graduate students and postdocs who are nominated to speak by their senior colleagues. Today, we have Enrique Gomez-Leos, who is a PhD student at Iowa State. We are happy to have him here today to tell us about a new infinite family of equiisoclinic tight fusion frames. Take it away, Enrique.
Right. Thank you, Joey, for the invitation and for the lovely introduction. So today I'll be talking about equiisoclinic tight fusion frames, and I hope that after this talk you can understand what they are and also how to construct some of them. So we'll begin with just a few quick acknowledgments. So this is joint work with Joey Iverson and Matt Fickus. I'll be presenting work that we did at AFRL in the summer of 2022. Okay. All right, so I'd like to start this talk off by introducing this problem. Fairly easy to understand relatively. So the problem is I have n lines in some d-dimensional vector space over, say, the reals of the complex, and I want these lines, which all pass necessarily through the origin, to all avoid sharp angles. All right, so I want to avoid sharp angles. And now, if I were Joey Iverson giving this talk, I would say that these lines are children in the backseat of my car. And I don't want the kids to be too close to each other because if they are, they tend to antagonize one another. So I want them nice and spaced out. Okay, so on the left is bad, on the right is good. So this is a geometry problem, but I understand better linear algebra, so we'll use the language of linear algebra to end this slide and throughout the talk. So the way we approach this is we consider n unit vector representatives from each of the lines. So I have n lines, n unit vectors. And the idea is that I measure out that sharpest possible angle, and I want to make that as small as possible. So it's really an optimization question. So while I won't be discussing this problem in particular, I'll be talking about a somewhat natural generalization of this problem. So rather than lines, we can think about lines to the origin, excuse me. Rather than thinking about lines to the origin, I'll be thinking about subspaces. Okay, so the question is, instead of lines, how do I pack in n subspaces, all of a fixed dimension R? So this is important that they're all the same fixed dimension R, in a d-dimensional vector space, again over the reals are complex. And now I want the angle between any two subspaces to be as wide as possible. I want to avoid sharp angles. So what do I mean by angles between subspaces? You know, there's lots of angles that you can probably form between subspaces, but I choose kind of maybe the most natural way. I take, say, lines from each of the different subspaces I'm measuring out, and I just measure that sharp angle. And I do that for all possible choices of pairs of lines. I measure out the sharpest possible angle between any pairs of lines from each of the different subspaces. And the way we do this with linear algebra is what we do is we fix orthonormal bases for each of my subspaces. So I have, W1 through Wn are those subspaces. And then I pick these phis to be orthonormal bases. And what I can do to measure out that sharpest possible angle I just described is I can compute the Gram matrix. That's this phi star phi j in the middle here. And I take the top singular value off that matrix. So this Gram matrix, if you haven't seen it before, the entries of this thing are just going to be like inner products across all vectors where those vectors come from each phi I and phi j. So I'll remind you, those things are orthonormal bases. And so the idea here is I want to minimize this parameter mu sub s. I want to, again, avoid sharp angles, just like I did in that one-dimensional case. Okay, so that's the statement of the problem. If we go to the literature, we actually have a we actually have a certificate of optimality. We have this is best possible. So you give me these W1 through Wn. I cook up some orthonormal bases. Doesn't matter which ones I choose. I just choose some orthonormal bases. That sharpest possible angle is always going to be as small as can be made no smaller than what you see in the square root here. So what the key of this slide is not that I have an actual number there, but I know when I could hit that lower bound. I have a characterization of how I can hit that lower bound, when I can saturate that bound. So just really quickly, I should mention that this lower bound does take into account the number of spaces n, the dimension of the ambient dimension d, and then the dimension of each of the subspaces r. Okay, but like I said, the key of this slide here is really understanding when I hit that lower bound. I hit that lower bound when the following two conditions hold. So the first condition is saying something about the gram matrix constructed by any pair phi j star and phi I, or sorry, phi I and phi j. I ask that phi j star phi I is a scalar times a unitary for all pairs I not equal to j. When I have this condition, I say that my ensemble of spaces is equiisoclinic. The second condition is kind of this weird thing about you take the orthonormal bases of corresponding to my subspaces and I stack them as column vectors to this matrix I'm calling bold phi. And I ask if this bold phi satisfies this property that phi star is a constant times the identity, where that constant's not non-zero. When I have that condition, I say it's tight. I say that this ensemble of spaces is tight. And together, I say that whenever I have that lower bound, meaning whenever I have those two conditions hold, I say that this collection of subspaces is an equiisoclinic tight fusion frame. Okay, so that's what these things are. They are a certificate of optimality. They're best possible. I'm avoiding sharp angles as much as I possibly can in some fixed d-dimensional vector space. Okay, so we'll be talking about a very special case about when we can construct these things when the ambient dimension is exactly twice that of the dimension of the subspaces. We'll go into that detail much later on, but first let's do some examples. So the first example I have for you is this 316 EITFF. So this is maybe a good introduction to what the notation means here. The 316 corresponds to the first integer tells you the dimension of the ambient space. So we're living in R3 here. The second integer tells you the dimensions of each of the subspaces. So here's 1. So this is exactly that first problem or the first question I talked about. These are lines because they're dimension 1. And then the third integer there, the n, tells you how many there are. Okay, so it's a 316. I'm saying there's 6 lines here. Okay, so how do you cook this thing up? Well, if you look at this thing is what we call a regular icosahedron. If you play some DND, this is also known as a D20. The way you construct it is by associating antipodal points to one another on that D20. Okay. This one is, however, not a choking hazard, though. You don't need this one. Okay. So anyway, here's a more exotic example. This is a 525, a real 525, so meaning that it's real valued entries. Unfortunately, I can't give you a nice picture here because here I'm talking about 5 different subspaces, the 5, 1 through 5, 5. And they're each 2-dimensional, living in R5, so pretty hard to visualize. So what I give you here is orthonormal bases corresponding to each of the subspaces. So maybe you should have you should be a little suspicious. Like, is this thing really an EITFF? Like, you just gave me some coordinates. I don't really see why that should be an EITFF. So we'll hopefully convince you that this thing is an EITFF. So that first condition was, I'll remind you, was equiisoclinic. I'm supposed to be able to take any pair of those phi's and construct their gram matrix, and it better be a scalar times a unitary matrix. Doesn't need to be the same unitary matrix for each one of them, but it better be unitary. So let's just arbitrarily choose 2 and 5. Okay, well, I get this nice matrix on the right-hand side here, and you could probably pretty easily in your head convince yourself that that thing's unitary, right? I mean, come on. And now, if I just check, sorry, got ahead of myself there. If I just check, say, phi 1 and phi 5, that thing, you see the entries of this thing, like, come on, it's 1/2, √3 is over 2s. That smells unitary to me, all right? And maybe phi 1 and phi 4, this thing, this is like a trust me bro moment because it's going to be kind of gross to compute the actual multiplication here. So just believe me that this thing is going to be 1/2 times the unitary here. Finally, the last condition was tightness. I'm supposed to stack these orthonormal bases as column vectors to this big matrix phi, this fat matrix phi, and I'm supposed to get that phi star as 2 times the identity. Okay, so maybe you should get the instinct that these things are hard to come by. You don't just kind of construct these things by accident. So I have 11 minutes left, and I think I have plenty of time to show you how to actually construct one of these things. So like I said, we'll be concerned about the special case of when the ambient dimension is actually twice the dimension of all the subspaces. So in this slide, we'll just kind of play around with an EITFF of exactly this type. So we're living in, say, reals are complex. I have this capital phi matrix that I've kind of just shown you an example of in the previous slide. those columns are going to be orthonormal bases corresponding to different subspaces. And they'll satisfy those two conditions, the equiisoclinic and the tightness condition. So what I can do is I can maybe think of this as like row and column operations. Without also generally assume that phi has this very special form. So in that first column, I see, or sorry, the first row, the first block row, I see it's a scalar times the identity for the first like n-1 columns. And the second row, I see that I get these scalars times these matrices I'm calling B. And then I get these scalars. Don't worry too much about those scalars. It will turn out that because this thing is an EITFF, that these B's kind of satisfy this property that they're like almost anti-commuting. They'd be anti-commuting if like the C was 0 here, if this constant was 0, but this constant is non-zero. So, however, the kind of the fascinating thing or the kind of the surprising thing is that if you look at the real span of these B matrices, so thinking about them as vectors, look at the real span of those B matrices, and I find an orthonormal basis for those for that real span. I call those matrices C. It will turn out that those C's do anti-commute. So if I look at, say I have M of them, I don't know what M is yet, but M is just some integer. These M's will be an orthonormal basis for the real span of those B's. And if I look at Ci Cj star plus Cj Ci star, I get 0 when I is not J. That's what I mean by anti-commuting. If you think about moving this Cj Ci star to the right-hand side and putting a minus in front of it. And then in the first condition, when I is equal to J, this is just saying that the C's are unitary matrices. Okay, so altogether, this one here, this equation 1, I'm going to call, whenever I find these C's, I'm going to call those solutions to Radon-Hurwitz equations. Okay, so I'll take a minute to talk about the significance of Radon-Hurwitz equations. And then after that, I'll tell you exactly how to construct these, an infinite family of these EITFFs. Okay, so as promised, this is kind of why maybe you should care about Radon-Hurwitz solutions, even if you don't care about EITFFs. It's because they correspond to these bilinear forms that have this special property that if I check out the norm of a bilinear form that corresponds to a Radon-Hurwitz solutions, it will turn out that computing the norm is the same as computing the product of the norm of each of the arguments. Okay, that's kind of a weird thing for a bilinear form to have. So this correspondence is pretty easy. So you give me these solutions, and what I do is I just fit f of x, y. I just define it to be the sum of multiplying by x on the left and then y on the right. So this thing will be a matrix, is what I'm saying. Like this thing inside the parentheses will be a matrix. So this is just going to be matrix multiplication on the right by a vector. I'll give you a quick example. So starting with these two C matrices, I'm claiming that these things are Radon-Hurwitz solutions, and it would be pretty easy to check. You just check that that they're in fact unitary and they satisfy the above defining condition. So let's compute the norm of the associated bilinear form, the norm squared, excuse me. In the blue here, I have exactly how I defined f of x, y. And kind of unraveling this multiplication, I squint a little bit and I see that in the middle there, I have x1, x2 are just scalars, and I have c1 star c2, c2 star c1. And together, those will cancel out because of the fact that the C's are Radon-Hurwitz solutions. In the blue here, I have that the C's are, it's just a restatement that the C's are, using the fact that the C's are unitary matrices. Collapsing those terms, I get x1 squared plus x2 squared in the middle there. And this is just the norm, the product of the norm squared. Okay, so but the real significance of these f's of these bilinear forms is really that they're somehow implementing in this case they're implementing multiplication over C. So if I kind of think about in this last little like line here, I think about these arguments as being complex numbers. Like this is like the first entry is like the real part of a complex number. The second entry is the imaginary part. This and if I were to work out, you know, the multiplication of x1 plus I x2 times this other complex number, I get exactly x1 y1 minus x2 y2 in the real part, and I get exactly x2 y1 plus x1 y2 in the imaginary part. So this is something old school. This is something like that was known to like Gauss. So there's a characterization that was done by Radon and Hurwitz, saying like for a fixed R. So R is that like dimension of these C's are all square matrices. They're all R by R. So given an R, like how many of these C's can I actually find? This answer was resolved by Radon and Hurwitz 100 years ago in the real case when the matrices are real valued, and it was handled in the complex case more recently by Adams, Likes, and Phillips in the 60s. So there's this row of R thing going on in the slide. It tells you if you pass in an integer R, the dimensions you want, I can tell you what's the largest possible collection of C's I can find for you. And it's in terms of these like 8A plus 2B things. It's not so important for the purpose of this presentation. Just know that I can compute this thing given an R. Okay, so where we're headed here is you give me Radon Hurwitz solutions, I cook up for you an EITFF. So let's see how that works. So as promised, given Radon Hurwitz solutions, cook up an EITFF. I'll use exactly the same Radon Hurwitz solutions that I started out with in that bilinear form example 2 slides ago. So you give me C1 and C2. And what I do is, where I'm going here is the spoiler here is that I'm going to cook up those B matrices, those kind of mysterious B matrices. The only thing I'm missing, so I have the C's. How do I go to get the B's? The idea here is to start off with a simplex. The simplex will provide us the coordinates. A regular simplex will provide us the coordinates to cook up the B's. So I always can find so in a space of dimension R to the M, in the space R to the M, I can always find M plus 1 vectors to form a regular simplex. So that's, in this case, it's I have M is equal to 2, and so I'll have a 2 by 3 matrix. So the column vectors of this S thing are exactly going to be the column vectors are exactly going to be kind of the points on this regular simplex. So starting off with that, now I just fill in the coordinates to the B matrices using the columns of S. So for instance, if I want B1, what I do is I just take the first entry of the first column, multiply by C1, and add to 0 times C2. So I get exactly just, C1 back, essentially. For the second one, I just look at the second column of S, look at the first entry, multiply C1 by minus a half, and then I add that to root 3 over 2 times C2. And then you'll see exactly, I get B2 there. So you can see that I do have that minus a half going on the diagonal, and the other 2 entries I see a minus root 3 over 2 in the top right, root 3 over 2 on the bottom left. B3 is done exactly the same, but now just using the third column of S. Okay, so now the B matrices. I had to scale them appropriately because I remember back when I was like playing around with these EITFFs, I had to scale them. So I just choose the appropriate scalars alpha and beta, and I just fit them in as column vectors to this capital Phi matrix. And now this capital Phi matrix will kind of encode the columns of this block matrix are exactly going to be the orthonormal bases for each of my subspaces that form the EITFF. And here it's easier to check if you like have MATLAB open or something. You can actually just put this in MATLAB and it'll and check those 2 conditions to make sure that this thing is actually an EITFF. But this is the construction. That's all it is. So starting with a solution to Radon Hurwitz equations, I can cook up for you EITFFs of where D is exactly 2 times R. And I can do it whenever I can find. So I can do it exactly whenever I can find those Radon Hurwitz solutions. So it's dependent on that fact. Moreover, I can start with an EITFF of parameters 2R, Rn, and then cook up solutions to Radon Hurwitz equations. This last bullet point, this B, is saying something about the automorphism group of an EITFF, and I'll just say I'll just say like a word about what that means. So if I think about my subspaces as just being represented by these little boring gray blocks, and I'm saying that the automorphism group is just going to be the collection of permutations for which I can find unitary vectors that actually implement like the permutations of those gray blocks. So you can think of like your favorite element from the alternating group. Say like I have 1, 2, the one that swaps 1 and 2 and swaps 3 and 4 and leaves everything else the same. I'm saying that I can find a unitary matrix that swaps that will actually multiply, that will actually swap phi 1 with phi 2, swap phi 3 and phi 4, and leave the rest of the matrices the same. Like leave the rest of the orthonormal bases the same. So that's what I mean by that every EITFF of this type has at least alternating symmetry. Okay. And that's all I have time for today. So thank you for your time.
All right. Let's thank our speaker with an appropriate button. Oh, there's a spaceship. Okay. And let's see, do we pause or stop the